Hello everyone, my name is Neha Kardam and this is the 7th lecture on Introduction to Microcontrollers. In this lecture, we are going to learn a small program. So let's get started. So the program which we are going to learn is the blinking LED. It's a very simple program in which the LED is going to blink and it stays there for a few seconds and then it will be turned off, and then stays there for a few seconds and then again turned on, so kind of creating a loop. So the first thing when you write the program, you need to make sure that you have an algorithm for that. So there are two ways to write the algorithm. Either you can use a flow chart or you can use a step-by-step process in the algorithm, which when I showed you in previous lectures. So like you write in a step form, like what you're trying to do before you write the main code. So, but for our this blinking LED program, I choose to go with the block diagram or the flow chart. So let's see the block diagram. So this is my block diagram for a blinking LED, and you can see that it starts with this oval shape box, which you know that is used for start and end or halt. So I'm using it for the start, and then second block indicates turn on the LED, which means LED will be turned on and then it will hold for a few seconds and then it will be turned off. So turn off the LED and then again wait for a few seconds and then it will go in a loop, and this process will go on and on. So use a block diagram to design a program before you write any code. So I use block diagram. You can choose any method. You can simply just write 1, 2, 3, 4 steps and then write what you are trying to do. For example, start the program. Second would be turn on the LED. Third would be provide a delay or wait for a few seconds or wait for 5 seconds or something like that. And then next step would be turn off the LED and then wait again and then create a loop. So that writing step process you can do, which is also called your algorithm. And in this flowchart, we use the flowchart to show our algorithm. Now, starting with start. So startup code will be different for each program and it depends on a number of things. For example, if you want to define the digital inputs or outputs, your start code is going to be different. And if you want to define like analog input or output, then your start program is going to be different. So there are a number of factors on which your start code will look like, and it will be different. So for us, we're going to see how it looks like. Now here, note that we are jumping past some of the setup. So what we are going to do is we are not directly going to go to this turn on LED. I'm going to show you something else and then we will come back to this block diagram. So this you have already seen in the last lecture, core or engine, and then you have like working resistor, and then you have bank 0, and in the microprocessor which we are using, it has around like 32 banks, and you have through this bank cell select switch, using this you can select the banks. So let's read here. Remember, the microprocessor can only do two things. So those two things are it can only move numbers and it can add numbers. So those are the two things which the microprocessor can do: move number and add numbers. And in this case, we are going to be moving numbers between the registers and between memory banks. So let's see our start code. This is our start code, and I hope you remember what are these like first column, second column, and third column means. So first column is basically your label. So this is your label, identifies as a section of a code, and second one is called your mnemonics or operator. So So operator, we use this term operator. The instruction to the pick is basically placed into this second column, and then we have the third column is called your operand. So this is operand, and this is where the operator is affected. So we're gonna see a step-by-step process, like what does all of these means. So starting with bank cell port A. So what this line indicates is that it's going to select a bank, and under the bank there is a port A register, and we want to use that port A register. So it tells the PIC to select the memory bank that contains port A. So bank cell is not exactly a instruction set. It's a compiler directive, but for now you can understand that it's kind of behaving like an instruction set. It is giving an instruction that to select the bank 0 in which we have port A, and we are going to use that. So this is what it says here. There is a huge difference between a compiler directive and the instruction set. So this is one of the compiler. This is the one of the compiler directive which is used, and there is a huge difference between this and the instruction set. So far you understand that we are moving we are moving to the bank 0. We are selecting that, and under that we are going to use port A. So this slide indicates the same thing. We have selected a bank 0. This is, you can see, is a bank 0, and then we have this bank 1. We do not need bank 1, so that's why the bank cell switch is not connected to bank 1. It is only connected to bank 0, and under bank 0 we have this port A. So the purpose of bank cell is to tell the compiler to set the bits inside the processor to allow it to use, and bank 0 is the one where the port A resides. Okay, now moving on to the next slide. So this slide says that the PIC can only access one memory bank at a time. So this is very critical thing. You have to remember that bank cell can select one bank at a time. And if you want to use something else, for example, I want to use this register address ADRESL. I want to use this register from bank 1. Then what do I need to do? I need to provide another instruction to my start code, or if to my start code, I will write bank cell. And then I'll put the name of this register. So automatically what will happen, this bank cell switch will be connected to bank 1, and it will basically use this register. So this is the same thing. You must somehow tell the processor to change banks when you need to access a register in a bank other than one you are currently in. So this is a limit of that of the part. Now moving on to the second part of second step of the start code. It says clear F port A. Now what does that mean? So clear F is the instruction. It is if you see into the data sheet, you'll get to know what this instruction set means, and we are also going to cover later on in this lecture. So for now, you understand, if you have a clear F, then it means it is going to move the literal number which is 00 hexadecimal to the port A. So in short, you can say that whatever, if you have any data in port A, so this port A has 8-bit register, and if you have anything before this instruction into port A, for example, if you have like 70 or 01 into your port A, then if you use this instruction, then this is going to clear your port A. So this will make your port A as 00. So all the 8 bits, they are going to be 0, 0, 0, 0, 0 and 0, 0, 0, 0. So that's why you use clear F. Anytime if you want to clear the register, you use this clear F. So we are going to clear our port A. Now let's see. So what it is going to do, it is going to take the instruction from this core or main engine and then move the literal number into using this bank's switch. It is already connected because we in the start program we already connected here. So it is right now at this position at connected to the bank 0. So it is asking that move this literal number to port A, and that's what it is doing. So let's read here. The move LW instruction places the literal number 0 cross 0 0 into the working register so that it can be moved into another location. So now moving on to the next slide. So it says bank cell tris A. So tris A is a register and it is used for selecting the port A. What does it mean? It means that using this tris A, whatever you put into tris A will decide whether your port A is an input or a output. So that instruction is already mentioned here. If you put 0 to the tris A, then that means your port A is going to behave as a output. And if you provide 1 to the tris A, then it means your port A is going to behave as a input. So in our case, if you directly see into the next step, it says clear F tris A, which means clear F means it is going to give 0 cross 0 0 to tris A, and that means we are giving 0 to the tris A, which means we are defining port A as output. So in our case, we are making our port A as output. Okay, so and the reason why we are making it output, I'll let you know in the next coming slides. Now, so yeah, clear F is going to do the same thing. As I said before, it's going to send the 0 cross 0 0 hexadecimal number to the tris A. So it will send this literal number to the tris A, and tris A also resides in bank 0, so you don't have to switch the bank. If you had some another register which belongs to another bank, then you might have to provide the instruction to select another bank and use another register. So here you notice even if you have to select the tris A, you used bank cell to get into this particular register. But I guess you can, even if you don't use it, you can still put the value into tris A. So this is something you can maybe try into your code, removing the bank cell, and directly after clear F port A, write down clear F tris A and see what is the effect on your tris A. So now moving on to this flow chart. So this start code we have already covered. Now we are going to move to this turn on LED code. So a look at the code in the next block, and note that as we add pieces of code, we may need to revise the block diagram. In this case, it's a tool for helping you to figure out how to write the code. So yeah, this block diagram, as I said before, it makes it easy to understand what you're doing into the code. So until now, we covered the start portion. We defined the output into our microcontroller, and now we are going to write the code for the LED on. So this is the code for turning on the LED. And it is very helpful if you write the proper label here. So for example, we want to turn on the LED, and that's why we use this label LED on. So for someone who doesn't know the program, they will themselves like after reading the label, they'll know that something it is related to turning on the LED, right? So if you use label, for example, set 2 3 or set _1 or something like that, so it would be a little bit confusing. So try to make your labels simple to understand. So now we will see this code, and we will learn like what does it says. So move LW. So what it is going to do is it is going to move the literal number to the working register. So move LW means move the literal number into the working register. This is our literal number. And now you might have seen, like, I use this type of notation. So this is one type of notation to express your hexadecimal number, or you can write 0 cross 0 cross 1 0. All right, so we have already seen this instruction, move the literal number this into the working register. Now before I move forward to the next step, I want to show you this picture. And you have the board already, development board, and this is the top view of the development board. And you can see what all these sockets and different uh, components on this board means. So for example, this is your reset button, and this is the 40 pin socket is there. This is the 28 pin socket is given into your development board. And then this is your header 1, and this is your header 2, and then you have push button 2, push button 1, you have potentiometer here, you have a USB connector here, and then these are your LEDs starting from D2 to D5. So you see D2, D3, D4, and then D5. Okay, so this is your Curiosity development board, and this picture basically shows your bank 0. So we have been talking about bank 0, and we have been talking about that we use port A, we use trace A, but where does that lie in the bank 0? So that's we are going to understand from this picture. So as you see, this is port A. So this we used, and corresponding to this, if you see, all of these are basically represents your bits. So if you have RA0, this represents your bit 0, RA1 represents your bit 1, RA2 bit 2, and then so on till RA7, which represents your bit 7. So starting from bit 0 to bit 7, and this is RA0 to RA7. So now I will quickly go back to the previous slide so that I'll show you where all these all these bits are on the development board. So if you look closely here, if you look closely to these points, you see this is RA0, this is RA1, RA2, RA3, RA4, and RA5. So when you activate the port A, these pins you can use, right? And these, when you use port A as output, then some of the pins are integrated with these LEDs, and whatever the code you put, these LEDs going to show that change in show that program. So for example, in our case, we are using blinking LED. So we are trying to turn on the LED and provide a delay, and then turn off the LED. So that's going to be basically, you will see that a result into one of these one of these LEDs. Now you may think, like, on which LED is going to basically show the change. So let's again go back to this slide. So you know that RA, RA0, RA1, RA2, RA3, RA4 till RA7. Okay, so we are going to put some data into this register. Okay, and whichever place we put corresponding to that, your LED is going to turn on. So I'll quickly go back to previous slide, and we are going to check what we are moving into the register. So we are moving this literal number to the working register, and this is our 0001 0000. So if you remember, this is so that's how you are going to relate. I'll quickly go to the next step also, because it says move the working register to the file register. Ultimately, this data is going to transfer into port A, and this represents your RA0. This is your RA1, RA2, RA3, RA4. So RA4, you are setting the RA4 to 1. and this is RA5, RA6 and RA7. So you are setting RA4 here. This RA4, you're setting a bit of RA4 to 1, and RA4 is here in this one. So it's here in this one. So corresponding to that, your RA4 is shown here. This is your LED RA4. It's going to turn on. So as I said before that we have like 4 LEDs. So if you see the number corresponding to each LED, you will get to know which LEDs you can use into your code. So this LED corresponds to RA4, this LED corresponds to RA5, this RA6 and this RA7. So we are using RA4, and if you want to make a more complex program, you can use all the 4 LEDs. So, but for this simple program, we are just trying to turn on this RA4 LED. Now, so you understand that this RA4 is going to be turned on. Now further looking into this bank 0, if you go down, you will see we have port B, and it also has 8-bit register. So instead of port A, you can use the port B also. But then you have one disadvantage that for port B, you do not have LEDs built in within the development board. You will have to use external LEDs if you want to show if you want to make the program for blinking LED. And then you have port C, and then you have further these resistor. So tris A we used, I hope you remember. So this tris A is used to turn on and to basically provide input and output, not provide, basically used to set the port A as input or output. So in our case, we have set the port A as output. And then you have tris B and tris C. And then tris B corresponds to port B, tris C corresponds to port C. So tris C will set port C as input and output, and tris B set port B as input and output. And that input and output depends upon what you are providing to the tris, whether 1 you are providing or 0 you are providing. Now and then later, if you go down, you have this LAT A, LAT B, LAT C. So these are the latch resistors. So whatever you write into these ports, it will be automatically will go to these, and it will latch into these resistors. Now again, moving on to the LED on program. So we move the literal number into the working register. So that's what we did here. Move the literal number into the working register. This is our working register. And then a second step says move the working whatever is there in the working register into the file register. And in the working register we have this number. So that number is going to be transferred into the port A. So port A will have a 0 cross 1 0. Now I will quickly go back to the third instruction, and it says call delay. So it will go to the delay instruction, and delay has its own code. So in this lecture we are not going to cover how the code for delay looks like. That is going to be another topic and will be discussed in the next lecture. But for now, understand we are calling a delay, and the purpose of delay is to provide a wait time on which your LED will be turned on. So at this point you have set RA4 as 1 in the port A, and it is if it is 1, then your LED will be turned on at this point. And then if you provide the delay, it will be turned on for a few seconds depending upon how long delay you have provided. So it's the same thing. So what have we really done at this point? So we have set the tris A register with 0 cross 0 0, which means we are making port A to be all pins set for output. Okay, so all the pins on the port A, they will be acting as an output. Loaded port A with 0 cross 1 0. So we have loaded port A with this number which toggles a pin logic high to turn an LED on. So on the development board, an LED is connected to port A. So after 4 to 7, which means RA4 to RA7, you have 4 LEDs, and I've already showed you on the picture, and that's what it says here. Now a subroutine call delay. So the call instruction jumps to a label in the code and executes from the start of that label. However, a call expects a return to this location at some point. So this is an unconditional branch with return. So and then we will discuss the code for this later on in the next lecture. And then the code for turn off the LED. So for that, just provide clear F, because clear F means we are giving 0 cross 0 0 to the port A. So if you provide this, port A will be all zeros, starting from RA0 to RA7, it will all be 0. And then you will call for delay because you want to turn off the LED for some time, right? So this label here is not as critical for the execution of the code, but it is handy as a marker to help a person follow what is going on. So even if you don't write this code, this label, and you directly write the code, connect this code after the LED on, it will still function. But then it's good to have this label because this shows to the reader that what is going to happen next, which means we are going to turn off the LED. So note that this is the same series of instruction we use to turn the LED on. So yeah, so clear F, you know that we have already used, and this also we have used in LED on. So this will move the clear F will move the 0 cross 0 from working register to the port A, and then it creates a loop. So you make a loop, and for that you can use a go to instruction. If you use the go to LED underscore on, then it will make a loop, and then this will go on forever. So go to is unconditional, and it will not remember where it came from and only jumps to the location specified. So let's see this. This is the whole code for our blinking LED. Only one thing is missing, the code for the delay. So that delay code I have not mentioned here, but I'll show you in the next lecture. For now, you just see that what we have done so far. We have used the start code, and then we have a LED on code, and then LED off code. So this you already know, LED on instructions you already know each step by step, and you know that after turning on the LED, it will provide a delay, and then it will turn off the LED, and then again provide a delay, and after that particular time of delay it will go to LED on. So LED on, which means it will go to this instruction, okay, and then we'll follow this loop, and then again go here. So you understand how to create a program on a microcontroller, and this language which we have used is your assembly language. Now we are going to quickly see some of the instructions we have used for this program. Starting with some opcode field. So in this program, we saw that we have seen this F. So for example, move literal number, move W to F. We have seen I think 2 times, which means move the number from whatever is there in the working register into the field register. So that F is your register field address, and it has this value. This is the address. And then this is the working register, you already know. B, if you have something B, you will see in some of the instruction sets. B stands for bit address with an 8-bit file register. K, you will sometimes see, which represents the literal field or constant data or label. X is, you may see sometimes, which is for don't care. It does not matter whether you have 0 or 1, the assembler will generate the code with X is equals to 0. It is recommended from form of use for compatibility with all microchip software tools. And then you have D. So destination select, when your D is equals to 0, then it will store the result in the working register. And if your D is equals to 1, it will store the result in the field register F. And then you have N, and then you have this MM. So do not get overwhelmed by all these terms. We are going to see its usage in the instruction set. Now I'm going to quickly show you the instruction sets which we have used, and you can find them also in the data sheet. So we used clearf, and this is how it shows in the data sheet. It has this syntax. You have some label and then clearf F. So this file register you have from 0 to 127. This represents your basically range, bit range. And then you have this F is your data saved is in operation is in hexadecimal, which is saved into file register, which means or you can say 00 hexadecimal number is basically sent to the file register, and file register will have 00 hexadecimal, and this Z represents your status register. So in this case, this Z status register will be affected, and Z is for your 0 bit. If you look for status register into the data sheet, you will see they are different status registers, and Z is one of them, and Z represents your 0 bit. So if you have Z is equals to 1, then the result of an arithmetic or logic operation is 0, and if you have Z is equals to 0, then it means the result of an arithmetic or logic operation is not 0. So in this case, we are sending 0 0, so logic operation is 0, and that's why you have status of 0 bit is equals to 1, or 1 is so this one is set to this status register. And then you have move literal to W. We use this instruction set. So move LW, and this K represents your literal number, and this is the range for K. And K, whatever is K you have, will basically transfer it to W, because that's what this instruction says, move L to W. And then it's done for one cycle. The 8-bit literal K is loaded into W register. The don't care will assemble as zeros. One quick example is also given. So move LW 0 cross 5A. And if you apply this, then after applying this, after instruction, you will have W is equals to 0 cross 5A. Okay. So you know that 5 is one number and A is another number in hexadecimal. Now we have this instruction, move WF. Move whatever you have in the working register into the file register. File register has this range 0 to 127, and this operation will be performed. Whatever you have in W will be transferred to F, and move data from W register to register, one cycle. And then, for example, if you use this as move WF latch A. So before instruction, let's see if your latch A has a 0 cross FF hexadecimal number, and your working register has 0 cross 4F. Then what will happen? This number, the working register number, is going to move into the latch A, because that's what it says, move W to F. So now your latch A has 0 cross 4F, because this is the same value. This has been transferred to here after the instruction is executed. Now next we have go to and call instruction set, and we have used these two instruction set in our program. Go to is an unconditional branch, and this is represented by this syntax. Operands is the lies between 0 to 2047. K is your literal number. Operation is K is PC. PC is your program control. and this is what it represents. And in this case, and this is your PC latch edge. And then in this case, there will be no status affected, and goto is an unconditional branch. This is a description, and the 11-bit immediate value is loaded into the program control bit. The upper bits of program control are loaded from PC latch edge, and goto is a 2-cycle instruction. So in short, you can say this goto is basically a kind of jump. And in this, if you use this instruction, then there is no return in this one. So there is no return instruction if you use the goto. And in this, the program control is transferred to a memory location, which is in the main program. And the value of program counter is not transferred to the stack in the goto instruction set. And then you have this call, which calls a subroutine. And this is the syntax for call, and this is the operands, and this is the operation. So you can, if you want to get in detail of what is happening here, you need to read the instruction, you need to read the data sheet, and then it explains you what is happening here. And in this case, status affected is none. And then I'll quickly read the description. Call subroutine, first return address PC plus 1 is pushed onto the stack. The 11-bit immediate address is loaded into the PC bits. The upper bits of the PC are loaded from PC latch edge. And call is a 2-cycle instruction. So all in all, you can say that call is a call basically calls the subroutine, and there is a return instruction in this one, unlike your goto unconditional branch or this instruction set. And that is the only difference. That is one of the difference actually, that this has no return instruction, whereas the call has a return instruction. And in this one, the program control is transferred to a memory location, which is not a part of a main program. And the value of program counter in case of call is transferred to the stack. So this is all about the instructions we have used, and there are many more instruction sets in the data sheet. Please look into the data sheet and go through all the instruction set. The more instruction sets you know, that you will have more power to use those in your programs. So this is the end of the lecture. Thank you so much for watching.